Aircraft manufacturers and regulatory authorities are anxious to reduce the number of incidents and accidents related to rejected takeoffs. In order to do this, we believe it is necessary that pilots have a better technical and procedural understanding of the issues involved so that they will be better equipped to take the appropriate decisions and actions on the line.
FAA studies indicate that up to the end of 1990, the world jet transport fleet had accumulated approximately 230 million takeoffs. They estimate that during this period, about 76,000 RTOs occurred, of which 74 resulted in incidents or accidents. The statistics indicate a rate of 1 rejected takeoff incident or accident per 3 million takeoffs. In 1995, the projected number of takeoffs is 18 million. If past performance is maintained, this will result in 6,000 RTOs, of which 6 will result in an incident or accident. Their data also indicated that over 75% of the rejected takeoffs were initiated at less than 80 knots, and only 2% initiated at speeds greater than 120 knots. Not surprisingly, most of the rejected takeoff incidents or accidents occurred in these high-speed events. The analysis of previous RTO incidents and accidents concludes that in about 58% of the cases, the RTO was initiated at a speed exceeding V1. In addition, nearly 1/3 of them occurred on wet or contaminated runways. The causes for the rejected takeoff incidents and accidents were also analysed. Perhaps surprisingly, only about 1/4 were due to engine malfunctions. Looking at the causes in greater detail, one can see that wheel and tyre problems caused a significant number of rejected takeoffs. The most significant statistic relating to these events is that analysis suggests that 80% of them were avoidable. Indeed, in 55% of the cases, the aircraft could have completed the takeoff and landed safely. Bearing these facts in mind, it's reasonable to assume that unnecessary RTOs might be reduced by improving training associated with the rejected takeoff. In particular, this training must address crew coordination and task sharing, a better technical understanding of takeoff performance, a better understanding of the reasons to reject the takeoff, and hence better decision-making, and improvement of technique. It's now time for a technical review. For a rejected takeoff, the most critical scenario is the runway or field length limit takeoff. What is a runway limit takeoff? In general, before FAA Amendment 42, it can be defined as the most limiting of the following 3 cases. Firstly, the all-engine go distance. That is 115% of the actual distance required to accelerate, lift off, and reach a point 35 feet above the runway with all engines operating. Secondly, the engine out accelerate go distance. This is the distance required to accelerate with all engines operating, have one engine fail at VEF, that is 1 second before V1, and continue the takeoff, lift off, and reach a point 35 feet above the runway surface at V2. Thirdly, the engine out accelerate stop distance. This is the distance required to accelerate with all engines operating, have an engine fail at VEF, 1 second before V1, recognise for failure, reconfigure for stopping, and bring the aircraft to a stop using maximum wheel braking with the ground spoilers extended. Reverse thrust is not used to determine the accelerate stop distance on dry runways. Airbus aircraft from the A320 onwards are in fact certificated to more restrictive rules. When the accelerate stop distance equals the takeoff distance, the runway is said to be balanced. Balanced runways optimise for takeoff in terms of weight versus V1. It also means that if an engine failure occurs at VEF, the aircraft will require the entire runway length to reach 35 feet if the takeoff is continued, or to stop if the rejected takeoff is initiated at V1. Analysis has shown that past accidents have occurred on runways that were longer than required for the actual takeoff weight. Combining this historical evidence with the demanding nature of high-speed rejects, it would seem prudent that the crew should always assume that the takeoff is limited by the accelerate stop criteria when the takeoff weight is field length limited. What is V1? What is the proper operational meaning of the key parameter V1 speed with regard to the stop-go criteria? V1 is determined from the pilot's first application of the first retarding means during the accelerate stop test. One common and misleading definition of V1 is to say V1 is the decision speed. This is incorrect, because V1 is not the point to begin making the operational stop-go decision. That decision must have been made by the time the aircraft reaches V1, or the pilot would not have initiated the RTO procedure at V1, and the aircraft would be travelling at a speed higher than V1 when the stopping action is initiated. If this is the case, and the aircraft is at a field length limit weight, an overrun is virtually assured. Conversely, if an engine fails at V1 minus 5 knots and the takeoff is continued, the aircraft will cross the end of the runway at about 18 feet. Pilots must consider V1 as the limit speed. A rejected takeoff must not be initiated after V1 unless the pilot is certain that the aircraft is unable or unsafe to fly. This applies no matter how much runway appears to remain. Remember, when the takeoff is continued following an engine failure, accurate handling is essential to achieve flight manual performance. What is VMCG? VMCG is the minimum speed at which, following the failure of the most critical engine, directional control can be maintained on the runway with the other engines at maximum thrust. It follows that V1 must never be less than VMCG. In some wet or contaminated runway cases, V1 will be limited by VMCG. Crew awareness when this occurs is important. Increased margins. The following items, which are not taken into account, add to the distance remaining for stop manoeuvres. Firstly, reverse thrust. On dry runways, the effect of reverse thrust is not taken into account. Secondly, flex takeoffs. Takeoffs utilising assumed temperatures for thrust reduction, known as flex takeoffs on Airbus aircraft, also provide an increased margin of performance that is not taken into account. This is due to the air density being greater at the lower ambient temperature during the takeoff than the assumed value. Hence, for a given indicated airspeed, the true airspeed, and therefore the ground speed, are lower. This leads to a reduction in the takeoff run, and to V1 being achieved in a shorter distance. This example indicates typical margins for an A310-304 series aircraft. Flap settings. Increasing flap settings ensures an additional safety margin for the rejected takeoff. A larger flap setting will decrease the takeoff speed and will increase the remaining runway length for the rejected takeoff. Conversely, the increase in drag at takeoff reduces the obstacle clearance and climb performance. Therefore, the choice of a larger flap setting at takeoff may be limited by the obstacle clearance, but it's always beneficial from a rejected takeoff point of view. These examples again are for an A310-300 series aircraft, based on a 10,000-foot runway at 2,000 feet elevation. You can see that as the flap setting increases, so does the margin available for stopping. Decrease margins. All accelerate stop distance computations assume that tyres and brakes are fully serviceable and efficient. But numerous RTOs have proved that failure and/or degradation of tyres and brakes jeopardise the RTO manoeuvre. In fact, Airbus Industry validate accelerate stop tests for 90% warm brakes, either by dynamometer tests or aircraft tests. In the case of a dynamometer test, the use of one reverser is taken into account. Secondly, blown tyres. Blown tyres are not a minor incident when encountered at high speed during the ground acceleration. When rejecting a takeoff with a blown tyre, the crew should anticipate that additional tyres may fail during the stop manoeuvre, and that directional control may be difficult. The decision to reject the takeoff following a blown tyre at high speed is still subject to some discussion, but if no damage is assumed, the go decision is preferable. Thirdly, runway surface conditions at the stopping end of the runway, that is, slippery conditions caused, for example, by rubber deposits. Fourthly, adverse slope during the stop. Only average runway slope is taken into account. During the flight test development program prior to certification, trials are made to determine the accelerate stop distances that can be achieved. These tests with a prototype aircraft are made under carefully controlled and recorded conditions by test pilots and can be considered the best the aircraft can achieve. The results of the rejected takeoff flight tests are analysed by the design office. They have established an accurate aircraft computer model which uses aerodynamic coefficients, brake characteristics and engine thrust. This model allows precise segregation of retarding forces during the stop, from aerodynamics, ground spoilers, engine and brake systems. It also allows the determination of brake torque and ground tyre limitations. This methodology, which is approved by the airworthiness authorities, has been used since the first Airbus aircraft certification and continues to be refined with each new member of the Airbus family of aircraft. The results from flight test and design office analysis are used to calculate the aircraft flight manual accelerate stop distances. However, line pilots are not test pilots, and additionally they are not expecting to stop. The authorities therefore require that margins are added to the flight test results. For example, for the A310-304 series aircraft, certificated prior to FAA Amendment 42, they look like this. The test pilot recognises the failure and applies the brakes after 0.6 seconds. The flight manual expands this delay to 1 second. He closes the thrust levers and the ground spoilers deploy 0.2 seconds later. To this, the flight manual adds 1 second. In both the test results and the flight manual expansion, the real-time response and actual evolution of braking efficiency is taken into account. Note, these margins are not designed to give the pilot extra decision time. Effects of failures or poor technique. It's important to understand the significance of failures or poor technique on the stopping distance. Here are some examples. Firstly, the effect of two inoperative brakes or two blown tyres. Notice the aircraft overruns the end of the runway at a speed of 75 knots and travels a distance beyond the end of 610 feet. Secondly, poor technique. Here we can see the effects of initiation of a reject 2 seconds after V1. Notice the aircraft crosses the runway end at 77 knots, travelling a distance of some 650 feet. Thirdly, the effect of using dry runway takeoff data on a wet runway. In this case, the aircraft leaves the runway end at 81 knots and travels some 710 feet. The external inspection. Verify the condition of the tyres and brakes, even on a short turnaround. The aircraft technical state. Verify before departure which, if any, deferred defects or MEL items will affect the takeoff performance. Takeoff performance calculations. Both pilots must calculate and verify the takeoff performance calculations and be aware of the takeoff limitations. Ensure you are prepared for the actual existing conditions at takeoff. The takeoff briefing. Ensure a thorough takeoff briefing is completed. An example will be given later. Taxi out. Don't taxi too fast. Be aware of brake temperatures. Runway lineup. Positioning the aircraft on the runway in preparation for takeoff is important. Pilots must use the correct lineup technique to maximise the distance available for a possible RTO. It's strongly recommended that operators include a correction to the available runway length on those runways where it is not possible to position the aircraft at the beginning of a published distance. Takeoff. Airbus strongly recommends the use of standard operating procedures, as detailed in the appropriate flight crew operating manual. Here are some highlights of the SOPs. The pilot flying announces takeoff and sets the takeoff thrust without undue delay. When the thrust is set, the captain places his hands on the thrust levers until V1 is reached. The pilot not flying verifies the thrust is correctly set and announces power set by 80 knots. He also announces 100 knots, thus alerting the pilot flying that he is now in the high-speed regime. He promptly completes the V1 call as V1 is reached. Malfunctions and the decision to reject. Airbus recommends that the decision to reject and the stop action be taken by the captain.
Stop. Reverse green. Past 80. Fox Tango, stop.
If a malfunction occurs during the takeoff, the captain calls stop or go. Decision management. Below 100 knots, discontinuing the takeoff should be seriously considered if any ECAM warning is activated. Note the speed of 100 knots is not critical, but helps divide the high and low speed parts of the takeoff run. Above 100 knots and below V1, rejecting the takeoff is a more serious matter. The decision to reject the takeoff should only be taken for a very few causes. Examples of failures that lead to a reject are given in the appropriate FCOM and include fire warning or severe damage, sudden loss of engine thrust, malfunctions or conditions where there are unambiguous indications that the aircraft will not fly safely, certain ECAM warnings which are not inhibited above 80 knots. In the event of tyre failures in the V1-20 to V1 range, unless debris from the tyres has caused obvious damage, it's better to get airborne, reduce the fuel load, and land with the full runway length available. If a failure above V1 occurs, the takeoff must be continued, as it might be impossible to stop the aircraft in the remaining runway. Task sharing during a rejected takeoff. The captain will call stop and simultaneously set the thrust levers to idle and select maximum reverse. The first officer will monitor auto-brake response and confirm reverse selection. It is not necessary to monitor the automatic ground spoiler operation. He will inform ATC and cancel any audio warning. As the aircraft comes to a stop, consider positioning the aircraft to keep any possible fire away from the fuselage. But remember, the priority is to stop the aircraft on the available runway. After the aircraft has stopped, the captain applies the park brake and then orders any appropriate ECAM actions. Use of the auto-brake system. A global assessment has been completed on the auto-brake and is sufficient to recommend that the auto-brake be used on all Airbus aircraft for the entire RTO manoeuvre until the aircraft comes to a complete stop. This procedure makes the RTO initiation simpler and prevents any inadvertent decrease of brake pedal pressure during the stop manoeuvre. Reverse thrust. Always select maximum reverse thrust on the available engines. Max reverse thrust is most effective at high speeds, as can be seen from this chart. The pilot not flying will confirm a reverse thrust selection. Remember, reverse thrust can be used until the aircraft is stopped if necessary. Use of toga. If the failure occurs at or after V1, the takeoff will be continued. In the event of a flex power takeoff, once the aircraft is under control following a failure, toga thrust may be applied at the pilot's discretion to improve takeoff performance.
The takeoff briefing is a vital part of a crew communication process and should be performed at an unhurried moment prior to engine start. The takeoff briefing should include the following items that relate to the safe conduct of the takeoff.
Nomination of a pilot flying. Use of engine or wing anti-ice and bleeds. A review of any MEL items which affect the takeoff.
Takeoff briefing, Frank?
Ready for takeoff briefing.
It will be a standard left-hand seat takeoff. The weather's fine, there's no requirement for engine or wing anti-icing. We'll be going with the packs on. The aircraft's fully serviceable, no need for an MEL reduction to the takeoff weight.
A review of the speeds, power setting, trim and configuration, making use of the MCDU and the PFD, the runway state and the surface wind. A review of the limitations.
Speeds, V1, 138, rotate, 145, V2, 152. Checked on the PFD. We're going with flaps 2, trim setting, 1 nose up, flex temperature, 39 degrees. The runway is dry, the wind is light and straight down the runway. It is a runway limited takeoff.
A review of the stopping procedure.
Call out any malfunction that occurs throughout the takeoff. In the event that the malfunction occurs before V1, I will call stop or go. In the event that I call stop, I will close the thrust levers, apply maximum reverse on the serviceable engines. You will monitor the action of the auto brakes, and if the auto brakes fails, you will inform me so that I can apply maximum braking with my feet and advise the tower that we are stopping. Cancel the audio if it's ringing, call 80 knots on the deceleration. You take no action until after the aircraft has been brought to rest. I've set the parking brake and I will then call for recon action.
A review of what to do if the takeoff is continued or the malfunction occurs at or after V1.
If I call go, or if the malfunction occurs at or after V1, the takeoff will be continued. No actions below 400 feet above the ground, which is 900 feet QNH for this departure. Apart from raising the gear, silencing the bell, and if you would remind me that Toga is available, I may elect to use it, as this is a flex takeoff.
A review of performance considerations and a review of altitudes. A review of the course of action once airborne.
I will continue flying at V2 or such better speed as we have to the engine out acceleration altitude, 2,000 feet on the QNH. Safety altitude is 3,000 feet QNH. If it's not an extreme emergency, we would intend to jettison fuel down to the maximum landing weight before making the arrival back here. Do you have any questions on the safety briefing?
Understood. No questions.
We recommend that this full briefing is given for the first flight of the day. Thereafter, the statement "standard emergencies" will suffice. In addition, a routine review of variable parameters should be made. During taxi out, confirm that the takeoff conditions have not changed and that the takeoff briefing and takeoff parameters remain valid.